Well, good morning, good evening, good afternoon to wherever you are today. In this particular lesson, I want to show you how you can use your TI84 calculator to take a function and graph it along with its first and second derivative, and how to interpret that correctly. Now, the application that I'm going to use uses colors for curves. You may have a TI83 or TI84 that doesn't have colors. This is still possible to do, but you've got a little bit of tracking that you have to do in order not to mix up which function is which. So you'll have to make sure that you understand which function is f, which function is f prime, and which function is f double prime. So what I've decided to do is I've decided to take number 47 with the given function. Now they said use a computer algebra system to graph f prime and f double prime over the stated interval. And so I am going to use the TI84. Use those graphs to make a conjecture about the locations and nature of relative extrema of f, and check your conjecture by graphing f. So okay, here we go. So what you're looking at right here are the three graphs, f, f prime, and f double prime. Can you tell by looking at the pictures which are which? It actually is possible, believe it or not, but probably at this stage you're going to have a little bit of difficulty. Okay, so the blue curve here is f of x. For those who may have color problems with their eyes, color blindness, watch my cursor. This right here that I'm tracing out with my cursor is f of x. The red curve is f prime of x, this curve here, and as you follow my cursor, this curve here is f double prime of x. Okay, so how did I get this thing to work? Well, let's go ahead. I'm going to clear out y2 and y3, and I'm just going to show you y1. Here's the function in question. 10x minus 3 is the numerator. The denominator is 3x squared minus 5x plus 8. Okay, how do I graph the derivative along with that? Here's what you do. You're going to use the derivative feature in your calculator. So you hit the math key, you go down to n derivative, which stands for numerical derivative, okay? And now this is important. You want the output to be a function of x. That's important. So this part right here needs to be x. That's the output. So when it takes the derivative, in the place of the variable, we're going to have a dummy variable, and I'm just going to use the letter a as a dummy variable. After it takes the derivative with respect to a, it then sets all of the a's in the function equal to x. That's kind of important. Okay, so derivative of the function. Now, I've already got y1 typed in, so what I do is I hit the vars key, I go to yvars, function, y1, and I make sure that it's a function of a. That's important. So differentiate this function of a with respect to a, and then after differentiating, set a equal to x, and that will make it a function of x. Okay, I've gone to the window. Make sure yours is -10 to 10, and then -2 to 2. Your scales are both 1. Hit graph, and then the first curve that's graphing here, this is f of x. And the second curve that's graphing here is f prime of x. Now it's going to operate slower than the first one because you've got to realize it's not generating an algebraic expression. It's using numerical techniques to find out what the values are. So it's actually creating a data set of ordered pairs. So the second curve that just graphed is actually not an algebraic expression that's stored in your calculator. It is a set of numerical ordered pairs that was generated by some technique programmed into the calculator. But now here's where we relate the function to its derivative. So where my cursor is, notice that the slopes of the tangent lines are negative, and they're kind of flattish, which means they're close to 0. And this is exactly the reason why the derivative curve is below the x-axis, because it's got to be negative, and it's why it's close to the x-axis, where y is close to being 0. As we come down, we find ourselves a local extrema. This would be a local min. And so the tangent line is 0 here, and that is precisely about where the derivative crosses. So, for example, if I did second calc and I wanted to find out where this minimum was for the first curve, I'm going to choose a point to the left of that minimum and hit enter. And then I choose a point to the right of that minimum. And then I let the calc method in the calculator do its business. And it's going to find out that the minimum is approximately at negative 1.202219. Now, if I want to figure out where the derivative crosses 0, it should also be at negative 1.202219. Remember that this is a set of ordered pairs that was numerically calculated. So most likely what's going to happen is it's going to give me a value that's close to that, jump to the other curve, but not exactly that, okay? Close to it, but not exact. So I choose a point to the left, I choose a point to the right, and I go ahead and I hit enter. I'm going to let it do its thing, and bam, there we go, negative 1.202221. And so that is very close. And so where it crosses the x-axis for the first derivative is also happens to be that x value where we have a local minimum. You can also see that happening here where we have a local maximum. And I believe also that this would be an absolute max since this would be the largest value of the function and this would be an absolute min. We'll notice right below it where the derivative crosses the x-axis is also the same x value for which the original function achieves the maximum. As we continue on following my cursor, notice the tangent lines are negative here and they're getting close to 0. So that's why we're below the x-axis here and we're getting closer and closer to the x-axis. So there it is. There's my first derivative graphed along with the original function. Okay? Now, in order to calculate the second derivative, I return to the math key, I go down, and I choose nderiv, again, for numerical differentiation. And I want that dummy variable, but this time I don't want y1, I want to differentiate y2, which is the first derivative. So I go to vars, yvars function y1, make sure that this is a function of a, and then after you differentiate that, oop, I said y1. What am I doing? All right, let's go back. Let's delete that. Vars, yvars, y2. Ha-ha! There we go. And then alpha a, close parenthesis. Ha! There we go. All right, and then after we differentiate that, we want to plug in x. All right, is there a way to see just the derivative? I really hope so. Let's see here. Color, ooh, I can change the color. I like that. All right, let's see here. Line, da-da-da-da. Let's make the first derivative dashed. And let's change the color here for this one. I don't like black, so let's choose green. And we'll make the curve, how about we make it a bunch of dots? Nah. Let's make it like that. Okay. All right, let's hit graph and let's see what happens. So here's the original function that's graphing right now. Then comes the derivative, the first derivative. Not too bad. And now comes the second derivative. And again, it's not going to happen as quickly because it's using numerical techniques to try and graph this curve. Okay. Notice the first derivative achieves some kind of local max right here, and right below it, as the dots come down, they cross the x-axis right about here, right beneath that. So that makes perfect sense because the second derivative, being the derivative of the first derivative, should do the same kind of thing that the first derivative does with respect to the original function. Okay, now where the function is below the x-axis, looking at the second derivative now, is when it's concave down. When it crosses up, it's concave up. So what we have here is actually an inflection point right here. And we can kind of see that happening right here. Following my cursor, concave down, and then all of a sudden, right at this point, this x value, it's now concave up. When the green curve comes down and crosses again and goes to negative is when it becomes concave down again. So some transition point or inflection point happens here, and now all of a sudden we've got a concave down curve. Coming up the function, the second derivative, it crosses here, and it becomes positive again, so that's concave up, which means somewhere around here is another inflection point, and that means that it's now concave up. And we can actually find out where those occur by using the second calc feature and figuring out when the second derivative is equal to 0. So we've just reaffirmed using our calculator how to find the local maximum, how to find the local minimum, all those extrema, along with inflection points. The function here is differentiable everywhere. And that is how you use, and that is how you graph a function along with its first two derivatives, or more, with your TI84. God bless you, wherever you are today.